Bismillahirrahmanirrahim. Dear students, today we are going to discuss the frequency dependent of permittivity. In this topic, we will develop a theoretical framework of anomalous dispersion. The frequency dependence of permittivity. First, discuss the dispersion in dielectric. You know, when a plane wave propagates through a simple dielectric with phase velocity v, which is equal to C over N equal to 1 over square root of mu into epsilon. Here we have assumed permittivity and permeability of the dielectric are constant, hence the phase velocity will be also independent of frequency of the wave. Mu is the permeability and epsilon is the permittivity of the material. But in real dielectric, the phase velocity would depend on the frequency of the wave, and this effect is called as dispersion. To explain the dispersion, we need to develop the more sophisticated model of the dielectric, taking into account the properties of molecules that constitute the material. What is dispersion? In simple words, you can say the splitting of white light by a prism shows that refractive index increases with increasing frequency. You can say that it decreases with the increasing wavelength. This phenomenon is called as dispersion, and the sportive medium is called as dispersive medium. For example, the blue light travels more slowly than the red light through glass and is refracted more strongly by a prism. In dielectric, waves at low frequency propagate with constant velocity c over square root of epsilon r. Epsilon r is the dielectric constant and it is independent of the frequency, but as the frequency increases, experimentally we will observe that the refractive index rises to maximum and then drops to minimum and then rises again. Experimentally we will get this type of behavior of the refractive index with respect to frequency. When frequencies are low or of the waves are low, we will have the normal dispersion in which the refractive index is independent of frequency. But as the frequency increases, you can see that refractive index rises to a maximum value, then drops to a minimum value, and then it rises again. This happens over a very low range of frequency, and this phenomena is called as anomalous dispersion. Experimentally, we find that anomalous dispersion is associated with absorption of the wave energy of the material. You can say that in this range of frequency, material absorb the waves, and this is due to the absorption of wave by the material. Many materials show absorption in infrared region. Almost all show absorption in UV region, ultraviolet region. Materials that absorb in the visible region appeared colored. In the gamma rays region means F is greater than, means frequency is greater than 10 to the power minus 19 Hz. All dielectric material become transparent and non-refracting. For X-ray frequency, when frequency is greater than 10 to the power 16 Hz, anomalous dispersion has stopped and refractive index of all the dielectric material will be exactly equal to 1. Now we discuss our model, Lorentz model, and this model is also called as electronic oscillator. Before this, we have ignored the atomic structure of the material. But now we will develop a simple atomic model of dielectric material to explain the variation of refractive index with the frequency of electromagnetic wave. We will find results in qualitative agreement with the experiments. For this model, you have to assume some features of the model. The first assumption is the medium is insufficiently dilute. Means the medium should be very sufficiently dilute. Your medium should be dilute that electric field by any given molecule is just the applied electric field itself. You can say if the material is dilute means molecules are far away from each other and the effect of Coulomb force on each molecule will be very small so that it can be negligible. Or you can say the field applied by other molecule being negligible or can be neglected. The second assumption is in the absence of applied electric field, the molecular dipole moment is zero, at least on average. And when the electric field is applied, some of the molecules charge more, some of the molecules you can say move away from their equilibrium position and achieve a dipole moment. You can see here when no electric field is applied here, the molecules will be in this form, and when a small electric field is applied, the material will be polarized. You can say the displacement of the, you can see here the displacement of the charge distribution. In this case, or you can say in this situation, the material is now polarized. The effect of electric field on the dielectric is to polarize the material. In a positive charge electron and a negative charge electron in an atom are separated by a distance delta x, then the polarization of the atom is P equal to E into delta x. You know the polarization, dipole moment is equal to Q into D. This is the dipole moment. Q is replaced by E and D is replaced by displacement or separation distance is replaced by delta x according to the problem. If there are n atoms per unit volume, the total polarization per unit volume will be written as, here you have just divided the dipole moment with volume, and n is the total number of atoms. Delta X is proportional to the strength of E, applied electric field, and the same direction as the field. The direction of separation is parallel to the applied electric field. Now, if you have considered the linear dielectric, then the polarization should be proportional to electric field, and epsilon into chi is the proportionality constant. When you replace the proportionality constant, you will have epsilon into chi e. Chi is the electric susceptibility. If electric field oscillates, then the polarization will also oscillate. If this factor is oscillating, then you know this factor should also be oscillating. In the case of electromagnetic wave, electric field is oscillating, so the polarization in this model will also be oscillating. Lorentz thought a model for electron in non-conductor which are bound or connected to a specific molecule or nucleus by an imaginary spring. You can say that this green color is representing the nucleus, and electron is here connected by an imaginary spring. The Coulomb force between electron and nucleus is replaced by imaginary spring. The spring would set into motion by electric field interacting with the electron. The field would repel or attract the electron, which results in either compressing or stretching the spring. You can say that the Coulomb force is here replaced by the Hooke's law. The force binding the electron and nucleus could be described by the Hooke's law. F binding equal to minus kx. K is the spring constant, which is replaced by m omega naught square. Omega naught is the natural frequency of the oscillating molecule. You in equation 4 you have written it in the differential form, and solution of this differential equation should be x t equal to a sine omega naught t plus b cos omega naught t. Here k equal to m omega naught square. These forces tend to derive the electron back to equilibrium position. Thus, this is regarded as harmonic force, all sharing the same natural frequencies omega naught. It means that you have considered a collection of atoms or collection of molecules, and all molecules will share the same natural frequency. All molecules will oscillate with the same natural frequency. Now we have a system of harmonic oscillators of natural frequency omega that are driven at a frequency omega by an applied force. The applied electric field will be oscillating and have this form: E equal to E naught into exponential of minus iota omega t, and E naught is the maximum amplitude of the electric field, and this is the oscillating part of the field. Due to this field, you can say the system of harmonic oscillator are driven at frequency omega. Omega is the frequency of oscillating field. As you know, the electromagnetic wave has also the part of magnetic field. It should also be oscillating, but here we have neglected it because the magnetic field in the electromagnetic wave also contribute a driving force on electron in the material, as F equal to E into electric field plus V cross B. For plane wave, you know, B approximately equal to E over C. Here you have assumed the velocity is very less than c, means the velocity of the wave is very less than the speed of light. As you know, when electromagnetic wave travel in the medium, its velocity reduces by its refractive index of the material. So here you consider the velocity is very small, so the contribution from the magnetic field is small, and you have only considered driving force in the form of electric field. Since the motion of charge will produce electromagnetic radiation, energy will gradually be removed from the oscillator, and the oscillator will damped. As we have considered the oscillating field, it means when you know that when the charge oscillates, the electromagnetic radiation will produce. So the oscillation should be damped, means it should be gradually diminished, or it should be gradually destroyed. We now we have to incorporate the fact through a phenomenological damping parameter, and gamma is the damping parameter, and damping force is written here m into damping factor, and this is the acceleration. No, this is the velocity. As you know, the damping force is equal to F equal is proportional to V. Damping force is proportional to velocity, and it should have the form of m gamma dx by dt for this problem. In the presence of an electromagnetic wave of frequency omega polarized in x direction, the electron subjected to a driving force, the driving force will be equal to QE, and E is the applied electric field. You have here applied the real part of the electric field, E naught cos omega t. E naught is amplitude of wave at point Z where electron is present. E is the charge of electric field. Now you have written the equation of motion. You have considered three types of forces in this model: binding force, damping force, and driving force. So the net force should be equal to ma according to Newton's second law. You have to put here the all these values, and binding force is equal to m omega naught x square minus sign is also applied here, and damping force is minus m gamma dx by dt, and driving force is here q e naught cos omega t. After rearranging, you have the equation 8. Our model describes the electron in a damped harmonic oscillator driven at frequency omega. Now you can say here you have the electron in damped harmonic oscillator, and the frequency of driving frequency is you can say the driving frequency is omega. Now you we have written the equation 8 in complex notation. Um, this symbol represent the complex notation. This is a differential equation, and the system, as you know, the system oscillates at driving frequency. So the solution of the this equation 8 should be in the form of equation 9, xt equal to x naught exponential of minus omega t. After inserting this in equation 8, we have the x naught is the amplitude of the driven harmonic oscillator. Q is the charge of electron, m is the mass of electron, omega naught is natural frequency, omega is the driving frequency, gamma is damping factor. The electron oscillates with same frequency omega as the driving frequency, and this happens at resonance. But the amplitude depends on the frequency. The constant gamma and the omega naught are the characteristic of medium which are to determine experimentally. At you can here we have explained that the at resonance omega naught and omega will be equal, and x naught will proportional to the omega, and you can say the damping factor, and these two can be find out omega naught natural frequency and gamma can be found by experimentally. Here you can see that this term is imaginary. If omega naught is greater than omega, then amplitude of the driven harmonic oscillator will be in phase in the electric field. But if omega or you can say the driven frequency is greater than the natural frequency, um, this term will dominate, and you can say that you have the imaginary contribution of the amplitude, or you can say a minus sign appear, and you can and the amplitude may be out of phase with the applied electric field. At high frequency, omega is greater than omega naught, amplitude and the E naught are out of phase. But at resonance, amplitude 90-degree out of phase with E naught. This is the amplitude. To find the polarization, we just multiply the charge of the particle, and now we have the form this. Just we have applied multiplied it with q, q square over m, this factor as it is, and epsilon, and phase vector also appear. You have to put here p equal to q into amplitude of the driving harmonic oscillator. If there are n molecules per unit volume, the polarization is given by the real part of. Here you have find out the dipole moment, and to find out the polarization you have to consider n molecules per unit volume, and this is the real part of polarization. Complex polarization is proportional to complex electric field. This is here written the complex polarization, and complex polarization is proportional to complex susceptibility and complex electric field. To find out the displacement vector, we have written d equal to epsilon e plus b. Putting the value, we have the equation 13. Now we have to find out the formula for the permittivity. So doing simple steps, we have equation 14. Now divide with equal to with epsilon naught. You will have the formula of dielectric constant, and this is the important formula for this topic. You have derived the dielectric constant, and now you have to derive the refractive index for the anomalous dispersion, and then we will plot these two factors and discuss the qualitative results. At resonance, omega approximately equal to omega I, the frequency of ER rises rapidly with the frequency and become complex. At resonance, when these two factors will be equal, the dielectric constant will become complex due to this factor omega, due to the iota, and this leads to absorption and anomalous, and we will discuss or we will describe it by qualitatively, means with the graph. In dispersion, in dispersive medium, the wave equation for the given frequency is written as, this is the wave equation in the form of electric field. As you have taken the dispersive medium, so here the epsilon naught is replaced by epsilon, and it is also written in its complex notation. It admits plane wave solution as before. In equation 17 you have written the plane wave equation. This wave equation 16 is the wave equation, and it should have the solution in the form of equation 17. Here z is the direction of propagation of the wave, means the wave is traveling in the z direction, and you can see here the wave vector k is taken complex. Now you have to all you can say that before you have derived the epsilon r, mean dielectric constant. Now you have to derive the wave vector in both in the complex notation, in from which you will derive the real value of the wave vector and the imaginary value of the wave vector. These are just the simple steps you can see here. Now we have derived the value of k square. This equation 19 present the complex notation, yeah, or we can say complex value of the k square. To find out the k, we just have to scale. We just taking square root. Um, but before it, we use the second term in large bracket is very small. Uh, Square root of 1 over epsilon equal to 1 over half over epsilon. Here you have used the binomial theorem. Now the k complex wave vector is equal to this omega over c into 1 over 1 plus n q square over 2m epsilon summation over j fj omega j square minus omega square minus iota gamma j. J is the number of electron. Fj is the you can say the Fj is also the number of the electron. Here you have taken Fj is you can Fj represent electrons, just electrons, mean one electron or two electron or okay. Now we have this. complex wave vector, any complex number can be written as the real part of it and sum of its imaginary part. So you have doing some simple steps and some simple mathematics. We have the real part of the wave vector and you have the complex part of the wave vector. We have just multiplied by two factor and then solve it. You or you can say that we have assumed that complex wave vector in the form of this equation, and then you have derived imaginary part and uh, real part. The right moving wave is therefore described by this electric field. Uh, Here you have written k in the form of complex wave vector ki. No, your k complex equal to, you as you know, k naught plus iota ki. After putting these, we have this form. This is more important factor in this electric field, and you have to discuss this factor. Wave speed traveling in z direction, phase velocity. Here we have derived the phase velocity as phase velocity is real, so you have to put the real part of the wave factor. Now refractive index, reflect in the refractive index you have also put the real part of the wave factor, as this is also a real quantity. This is the important formula of refractive index. At low frequency, when omega j is very greater than omega, when omega j is greater than omega, um, you will have the form of this. You can say that the refractive index will be equal to 1 over n q square over 2 m epsilon into m omega j square, and it should be very greater than 1 when the frequencies are low. But at high frequency, the refractive index should be equal to less than 1. The intensity of electromagnetic wave is, as you know, is proportional to E squared, the electric field square, and you have to put here the formula. Um, this exponential factor this exponential factor goes to 1, and you can say that intensity is approximately equal to exponential of minus 2 kiz. This is the attenuation factor. You have assumed that alpha equal to 2 ki, and this is the absorption coefficient. The wave is an exponentially decreasing function due to dissipation of the energy. This factor represents the dissipation of the energy or dissipation or attenuation of the wave intensity. It means due to this factor, the intensity um, will be abolished when wave passes through um, when wave passes through the material up to distance z, and this z is this distance z is known as skin depth. The imaginary part of the dielectric constant is associated with the absorption of electromagnetic wave, and we have derived this result from the this formula. You can say intensity is proportional to exponential of minus alpha z. This represents the absorption of the wave intensity. Um, the largest absorption occurs at resonance omega equal to omega ji at high frequency when omega is very greater than omega j, ki and k tends to 0, therefore medium become transparent. And from you can find out these values or these behavior of alpha and k with the plot. Here alpha the value or you can say the formula of alpha is written here. Alpha equal to qi, and just you have multiplied ki with the factor 2. Now discuss the plot of refractive index and imaginary part, the real part of the refractive index and the imaginary part of the refractive index. The blue plot represents the imaginary part of the refractive index, that is the alpha. Here you can say at low frequency alpha is negligible, but at high frequency it rises up to maximum, and maximum value is obtained at omega equal to omega j, means this happens at resonance. After this, this value on this graph drops down to again 0. This behavior is known as the absorption of the wave, and this happens at the resonance frequency when omega equal to omega j. This you can say this behavior is called as anomalous dispersion. Now see the behavior of the refractive index. You have to you here plot the refractive plot, or you have plotted here n minus 1. Here you can see at low frequency it has the constant value, that is n q square 2 over 2m epsilon into omega j square, but at resonance frequency it drops down to 1, and then it has the minimum value at some value of omega, and then it rises again. At resonance it have the, this is the behavior at resonance, and at resonance when omega equal to omega j, this the refractive index goes to 1. This value is okay. But as you have plotted here n minus 1, so you can say that at resonance it dropped down to 0, then it have its maximum minimum value, means it become negative, and then when the at high frequency it rises again. Behavior of alpha. Alpha peaks at resonance, omega j smalls elsewhere. At a non-zero value of alpha tends to attenuation of the wave in the dielectric. The energy of the wave is transferred to the material. Here, in the anomalous dispersion, the different behavior of n and refractive index and alpha is due to the attenuation of the wave, and attenuation happens when the wave is absorbed by the material through which it is passing. I have already discussed the behavior of refractive index in the graph. Here we have concluded when omega is less than omega j is the resonance frequency, and normal dispersion happens, and it means as the frequencies rises, refractive index also rises. When you can say that attenuation or dispersion, yeah, or absorption of the wave is equal to 0. Refractive index increases with frequency with no absorption. But second case is at resonance when anomalous dispersion happens, refractive index drops down as frequency increases, and this happens due to the absorption of the wave when alpha is non-zero. And above the resonance frequency and again is less than 1, and absorption is approximately equal to 0. We have concluded in the neighborhood of resonance, the index of refraction drops sharply. In the neighborhood of refraction, in the neighbor, you can say in the neighborhood of resonance, the index of refraction drops sharply. This is the conclusion, the main result of the topic. Again, see the region. In the region omega is less than omega and greater than in the region omega and less than omega 2, this region omega 1 to omega 2. with the region of is the region of anomalous dispersion, that is the material is practically opaque. In this frequency range, the material is practically opaque. This results in colored material. And what is the reason? The amplitude of vibration of electron is very large at resonance, and large amount of energy is dissipated by the damping mechanism, and this is all happens in the anomalous dispersion. In the end, I have written that all substances have more than one resonance frequency. In the quantum theory of atom, the resonance frequency are associated with transition of electron between energy levels. Away from the resonance, damping can be ignored, and then you can write refractive index in the form of this equation. For transparent medium, when omega is very less than omega j before the resonance, the refractive index can be written in this form, and you have replaced it with coefficient a, and this is replaced with coefficient b. In terms of wavelength in vacuum, lambda equal to 2 pi c over omega, n equal to 1 over a into 1 over b over omega square, lambda square. A is the coefficient of refraction, and b is the coefficient of dispersion. This is known as Cauchy formula, and you can derive it when you have ignored the resonance or damping of the wave in the material. I hope the topic I have you have clearly understand the topic. Class, Allah Hafiz.